students, welcome back. This is Torres, elbow bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email and I'm happy to help in whatever way I can. So lucky you, you get to hear my voice for another lecture. But the best part is we will be calculating population and sample variance. Yay! Let's start with a quick review. Remember, we started discussing how mean, median, and mode are all measures of central tendency. And measures of central tendency tell us how our data is like. Measures of variability describe how the data is different. The most commonly used measures of variability in statistics are range, interquartile range, variance, and standard deviation. Range is just the difference between the maximum value in the data set and the minimum value within the set of data. So in this example that I've used several times, the maximum value is 6 and the minimum value is 3. So 6 minus 3 is 3. Our range is 3. The interquartile range is the middle 50% of the values. To find the interquartile range, we use the 5-number summary. To find the interquartile range, we take this hinge of the box, which is the third quartile or the upper quartile, and from that we subtract the lower quartile, which is this hinge of the box. The lower quartile is also called quartile 1. When you subtract the third quartile from the first quartile, you get the length of this box right here. Somewhere in the box, you'll also have a line that describes where the median is. So the interquartile range uses the median as a central value. Also, the interquartile range is not sensitive to outliers. So this outlier over here is really not affecting the shape of this box in any way. It does give us a reasonable understanding of what the spread of the data is, but it really ignores the majority of the data. It shows where the typical values exist within the center of the data set. However, the IQR is not used very much, so a general audience may not have an idea of what you are referring to when you work with interquartile range. Variance and standard deviation use the mean as the central value, which is something that more people are familiar with. The variance is the measure of how far the data is spread out from the mean in squared units. And the standard deviation is the measure of how far the data is spread out from the mean in linear units. The variance is not directly comparable with the mean because it's reported in different units, whereas the standard deviation is in the same units as the mean. Let's discuss the idea of squared units a little bit more. Remember these squares that we talked about when we did the review on powers and roots? And we saw that when you square a side, right? In this case, we have a length of 2 times a height of 2. 2 times 2 is 4, and it gives you the shape of a square. There are 4 squares that are comprised within this bigger square inside of it. So the pink covering, the pink area, is an actual square. The variance works that way because it's in square units. It's really discussing an area that is being covered up, whereas the standard deviation is like the sides. Okay, so when we're discussing variance, remember that we're talking about an actual area that has a width and a length. Here are some dogs, okay, and we wanted to measure the height of these dogs. So we have 1, 2, 3, 4, 5 dogs. And the mean or average length of these dogs is 394 millimeters. And right here, if you can see it, there is this green line that marks right at 394 millimeters. If you took the difference of the height of each dog to the shoulders relative to the mean, so you're taking the difference of the height of the dog and the mean, here on this tall black dog, this tall black dog is 206 millimeters taller than the mean. This orange skinny dog is 76 millimeters taller than the mean. This little dachshund, it's 224 millimeters less than the mean. this little schnauzy looking dog is just a little bit taller than the mean, only 36 millimeters taller than the mean. And then this little, I don't know, French bulldog or whatever that is, here's his shoulders, and he is 94 millimeters less than the mean. So we've got the black dog is taller, the skinny dog is taller, the wiener dog is shorter, quite a bit shorter, the little schnauzy looking dog is a little bit taller, and the French bulldog dog is a, you know, quite a bit shorter, but not as short as the little dachshund. Okay. And these. Now, see how this is a distance? It just gives you the difference between the mean and the height of the dog. If we were talking about variance, we would be talking about square units. We would be talking about an area of difference. And that doesn't really make sense when we're talking about the differences between the height of the dog, of each of the dogs, and how that compares to the average height of the dogs. The idea of a length in one dimension has more meaning. So let's continue talking about variance. Variance describes how spread out the data is for the mean in squared units. Okay, so we can calculate the variance for a population, or we can calculate the variance for a sample. It really just depends what you have access to. If you have access to the population, then you would calculate the population variance. If you're working with a sample, then you're going to work with a sample variance formula. The reason for the two is to account for error that might exist when you only have a sample instead of the whole population. If I want to calculate the population variance, that means that I have to have all the individuals that make up that population in order to take measurements and be able to calculate that variance. If I only have some of those people in the population of interest, then I'm working with a sample. If I'm working with the population, I will know the truth. There is no room for error. If I take careful measurements and do the calculations correctly, I know what the true variance of that population is. The calculation is a parameter because I'm using population data to calculate the variance. Let's look at an example. So this data represents the travel times in minutes to work for all 7 employees of a startup web development company. Okay, so there's all the employees that work for this company go to work, and they measure how long it takes them to go to work. This person takes 23 minutes, this person 36, this person 23 minutes, this person 18 minutes, this person 5 minutes, this person 26 minutes, and this last person is 43 minutes. Now, the reason why this is underlined is because I'm trying to impress upon you that these are all the employees that work there. It isn't some of them, it's all of them. I can know what the true variance is for these employees for this company because I have all the data. So I'm going to go ahead and use this data to compute the population variance. So I've gone ahead and pasted the question into Zite Board. Remember, the Zite Board will be linked below in the description box. And I've made myself this little table. I have pasted the population variance formula into Zite Board as well. Before we start, I want to discuss some of these symbols so that you can be clear on what they mean. The first symbol I want to discuss is this one that looks like a little cursive O with a square. This is sigma squared, and this means population variance. I'm just going to put pop variance. The X is the actual measurement, the data point. The raw data. These right in through here. The mu, how that looks like a cursive U, is the population mean. And big N is the size of the population. Okay. So let's go ahead and read our question. The following data, n equals 7, represents the travel times in minutes to work for all 7 employees of a startup web development company, and it has all the data right here. Compute the population variance for this data. Okay, so I'm going to start off by writing all my x's, these are all x's, I have 7 of them, into this table that I've created. And I'm going to just go ahead and do this in blue. So this is going to be 23. The next one is going to be 36. The next one is 23 again, 18, 5, 26, and 43. Okay, great. So this is right here, all my individual data. Now I'm going to compute the population mean, and I can do that using my Google Calculator. So here's my Google Calculator. I'm going to do 23 plus 36 plus 23 plus 18 plus 5 plus 26 plus 43 equals, and then I'm going to go ahead and divide by 7. Divided by 7 equals. And I get that the mean for my data, population data, is 24.857. So I'm just going to say it's 24.9. Notice that I have rounded. So I'm going to say it's 24.9. And that is the mean for all of this data. Great. Okay. This next column says, what is the difference between your data and the population mean? Okay, well, just by comparing this, think back to the dogs, right? This is the green line in the dog example, and these are the heights of the dog. So this is a little bit less than the mean. This is a lot more than the mean. This is a little bit less than the mean. This is a lot less than the mean. This is a whole bunch less than the mean. This is slightly more than the mean, and this is a lot more than the mean. So we're going to go ahead and just subtract the x from the mu so that the sign, either positive or negative, will tell us if something is less time or more time. So I'm going to go ahead and pull over my calculator again and clear this out. And I've got 23 minus 24.9 equals, and I get negative 1.9. I'm going to go ahead and write that in, negative 1.9. And I'm going to go ahead and do that again. I'm going to clear this out. And 36 minus 24.9 equals 11.1. So that travel time is a lot more than the mean, 11.1. This next one is going to be the same as it was up here, so negative 1.9, because I've already calculated it once for 23. So I'm just going to copy that to save time. Let's see what's happening with 18. So here I'm going to clear this out. 18 minus 24.9 equals, I get negative 6.9. Okay, clear this out again. Clear. 5 minus 24.9. Now this is going to be negative. It's a lot different because what are we saying? It takes, on average, it takes people 24, almost 25 minutes to get to their work. And this person, it only takes them 5 minutes to get to work. So it's going to be a lot less. Negative 19.9. Okay. 26. Clear, clear, clear. 26 minus 24.9. We know that's just going to be a little bit of a difference, 1.1. And then this last one is going to be a lot different because this usually on average it takes people almost 25 minutes to get to work, and this person it takes a whole 43 minutes. So we're going to clear. 43 minus 24.9 positive 18.1. Okay. So here we have the differences between each piece of data and the population mean. Now, I rounded these numbers, if you recall, because my original mean was out many places, and then I rounded to 24.9 just to try to keep the arithmetic a little bit more simple. But let me share with you an Excel spreadsheet that I did that did not round very far out. Okay, so here is my Excel spreadsheet. If you notice, this Excel spreadsheet did not round my population mean. It still gave me the 24.857 that I had when I did it by hand, but this time I went ahead and left it here so you could see that I didn't round. And then in this one, this is just the difference between X and the mu. So here I have negative 1.857, whereas here I have negative 1.9. So notice, so basically what I've done is instead of rounding it like I did here, I've kept it all going out as far out as it would go until I started getting all zeros. If I took the sum of all these, if I summed them, look at right here what I got. My sum equals 0. My sum equals 0. That means that this 23 minutes was a little bit less than the average, right? This 36 minutes was a lot. This 23 was a little. This 28 was, you know, a little bit less, not a whole lot. This 5 was a whole lot less. This 26 was a little bit more, and this 43 was a lot more. So by things being a little bit more and a little bit less, it all evens out so that there is no difference. So that the sums of the differences come out to 0. That's what levels everything off. If I were to add this up and get 0, I don't have a lot to work with. So in order to continue to work with my calculation, what I'm going to do is I'm going to square each one of these values so that when I sum them up, I will actually get a value. I will not get 0. So let's go ahead and square all of these. I'm going to grab my Google Calculator again. Where's my Google Calculator? Here he is. And I'm going to go ahead and start squaring all these. So 1.9 times 1.9, and I get 3.61. Okay, so I went from something being negative to something being positive. Now I'm going to take 11.1 and square it. And I get 123.21. I'm going to get negative 1.9 and square it again. So again, I already did that, so I'm going to get 3.61. See, I did it before. Now I'm going to go ahead and square negative 6.9. Mm. $47.61. I'm going to go ahead and square negative 19.9. $396.01. $1.1 times 1.1, and I'm going to get 1.21. And 18.1 times 18.1, I get 327.61. Okay, so now these are my squares. So these are, let's go back. This is my data. This is my population mean. This is the difference between my data and the population mean. This is also called deviations from the mean. It just means differences from the average or differences from the mean. And these are called squared deviations. Okay, so what I've done is I've taken my deviations and I've squared them. Makes sense. Remember that variance is in squared units. So now I'm working with squared units and I can add all these up and get my sum of squares. Sum of squared, that's what this symbol is telling me to do. It's saying that when you get your squared deviations, add them all up. So I'm going to do my sum of squares. And I'm going to add all of this up. So I'm going to go ahead and clear this out. Clear. 3.61 plus 123.21 plus 3.61 plus 47.61 plus 396.01 plus 1.21 plus 327.61 equals. I get 902.97. Oops, 87. Let's correct that real quick. 87. Okay. So this is my sum of squares. So what have I done? I have taken my data point and I've subtracted the mean. That is all of this. Then I squared that. That is all of this. Then I added them all up. That is this number here. Now I have to divide by the population size. And I know from up here that my population size is 7. So in order to find the variance, I'm going to take my sum of squares, (902.87) divide by 7, and I'm going to get that my variance is 128.98. Okay, this is my population variance. Why? Because I had all the data. I had everybody that worked at that company. I was able to take the information of how long it took each of them to get to work, and I was able to calculate the true variance for the population, for everybody that worked there. This was not a sample, that was everybody that worked there. As I've been doing, I also have all the calculations in the Google Slides, which I have linked in the description box below. So here is the question that we had. Here is all the information written out. Notice that this is just rounded up to the nearest whole minute, which is 129 minutes, but it's minutes squared. Like, what is a minute squared? We don't talk about minutes squared. We talk about minutes. So do you see why the variance unit doesn't really make sense within the context of this question? So if we were going to just make a list of how to calculate the population variance summary, first, we know that the variance is a measure of how far the data is spread out from the mean in squared units. You take the difference of each data point from the mean. So you find the deviations for the mean. To make it positive, you square those deviations from the mean. And then you add all the squared deviations up, and divide by the number of data points within the population. The symbol sigma squared is used to represent the population variance. So like here, we've got sigma squared is equal to the sum of all the squared deviations divided by the number of data points in your data set. Remember that the units for variance are the square of the original units and are often nonsensical. They don't make sense in the context of the problem. Now let's go ahead and use StatCrunch to do a sample problem. We're going to go ahead and use the same data that we used a little while back on Professor Salaries to calculate variance for a larger data set using technology. Okay, so I've got this doctoral salary information, and I'm going to go ahead and highlight the areas that I need here. Right click and copy, go to StatCrunch, and remember you click where it says var1, and I like to use Control V to cut paste everything. If you're working with a Mac, you would use Command V. Okay, so I have my information here, and I want to do descriptive statistics for a population variance. Okay, so I'm going to go here where it says stat, go down to where it says summary stats, and go over to where it says columns. And since salary is my only quantitative variable, it's already selected it there. Okay, so here I get down to the choices that I have. I'm going to go ahead and click N because it's always a good idea to know how many data points you have. And I'm going to go ahead and hold down Control and hit mean. Now this next one says variance. This is for population variance. Do not use this one. This is for sample variance. If you want to calculate variance for a population, you would go to unadjusted variance and go ahead and click compute. And here I have my unadjusted variance is 4.26. Okay, so it's super easy to do with technology. Obviously, we're talking about 87 pieces of data. I'm not going to have you find the deviations from the mean and square the deviations and then add all these 87 squared deviations up so that you can divide by 87 and get the unadjusted variance. For a larger data set, I would give you the technology to work with. Okay, so that's population variance. Let's talk about sample variance. So sample variance works the same exact way, except instead of dividing the sum of the squared deviations by the number of data points that you have, you're going to divide the squared deviations by the sample size minus 1. Okay, and the purpose of doing this is to change the denominator and adjust for possible error. So you already know you're going to have error because you don't have all the possible values, all the individuals that fit within your population of interest. You're trying to make an inference. So here we're working with the same 7 employees again. Okay, these were the all 7 employees that work in the startup, but they've decided to do a random and independent sample of the employees here. And they drew 3 people randomly and independently, and the sample of the travel times were 5, 26, and 36, and they want you to calculate the variance for the sample. So this is going to be sample variance, not population variance, because you're not working with everything, you're just working with a select few. So again, here I've gone to Zite Board. Don't forget that this Zite Board link is in the description box below. So here is the problem. Of all employees, a random and independent sample of travel times n equals 3 was selected. The sample of travel times were 5, 26, and 36. Calculate the variance for the sample. Okay, awesome. Here I have my sample formula. Let's go over what the little pieces mean in more detail, just like we did for the last one. Okay, I'm going to do this in red again. So this time, instead of having sigma squared, we have s squared, and that is the sample variance. Here I have x again. X is my data. It's my individual pieces of data. So here my X would be 5, and another one would be 26, and another one would be 36. X bar is the sample mean. N is my sample size, which is 3. Okay, so here let's write down all my X's. So here I have 5, 26, and 36. Great. So let's find the mean for these 3 pieces of data. So I've got 5 plus 26 plus 36 equals, and I'm going to go ahead and divide by 3, and I get 22.3. So I'm just going to go ahead and say 22.3. Now this makes sense, right? Because we've got this number, which is a lot less than the mean, this number, which is a little bit more than the mean, and this number, which is a lot more than the mean. Don't forget, I've rounded here so that I could make the arithmetic a little bit easier for us, but there is error every time I round. So I'm just rounding to make this a little bit easier for instructional purposes. Now I'm going to subtract the mean from each one of the data to get my deviations from the mean. So here I'm going to take, clear this out, clear, 5 minus 22.3, and I'm going to get negative 17.3. Okay, this next one, I'm going to clear this out, clear, 26 minus 22.3, and I get 3.7. Here I've got 36. 36 minus 22.3 equals 13.7. Okay. Just as before, I wanted to point this out to you that when I did this on Excel, I was able to not have to round here. So I went ahead and just left it as it was actually given, no rounding. When I take the deviations from the mean and then they get added up, you get 0. So remember, when you add the deviations from the mean, you just end up getting 0 because the whole point of an average is leveling everything so that the same amount is distributed evenly amongst all of the individual cases. All right, now we can start squaring the deviations from the mean. So let me go ahead and grab my Google Calculator again. And I'm going to go ahead. The last time I did this, I'll have to apologize, I didn't actually use the negative sign. So this time I'm going to be a little bit more careful. And I'm going to clear this out. And I'm going to do parenthesis negative 17.3, close parenthesis, and then I'm going to go ahead and square it. And I get 299.29. All right, and then I'm going to do 3.7 squared, clear, 3.7 squared, and I'm going to get 13.69. And this last one, I'm going to go ahead and do 13.7 squared, and I'm going to get 187.69. Now notice all of these columns and cells are blank. They're blank because I didn't need them. I used all 3 of my values. I only had 3 right here. Okay, great. Now I'm going to go ahead and start adding up the squared deviations. So I'm going to take all these numbers and add them all up. So let me go ahead and bring this over here. I'm going to go ahead and clear everything out. 299.29 plus 13.69 plus 187.69 equals, and I get my sum of squares equals 567. Okay, 567. Awesome. I'm going to scooch this up just a little bit. So I have my sum of squares equals 500.67, I think. Yes. Okay. Now my variance, let's go back up here and look at my formula. I took the deviations from the mean. It's here. I squared them. It's here. Remember, this sigma means add everything. So I summed everything that I had just finished squaring, and I got 500.67. Now I'm going to divide by my sample minus 1. So my sample minus 1, n minus 1, is the same as 3 minus 1, which is the same as 2. So I'm going to take my sum of squares, and I'm going to get that my variance equals 500.67 divided by 2. And if I go over here and I divide this number by 2, I get 250.34. And this is my sample variance. So, as I have done in previous examples, I've gone ahead and written everything out. Again, we get 250.3 square minutes. We don't usually talk about time in square minutes. We just talk about minutes, right? Time is a linear type of measurement. So while we did compute the variance correctly, the context is nonsensical. It doesn't make sense. As a summary, variance is the measure of how far the data is spread out from the mean in square units. The difference from the mean is the data point minus the sample mean. That's called deviations from the mean. You square the deviations from the mean to get a value that is positive, and then you add them all up to find the sum of squares. Once you find the sum of squares, then you divide by the sample size minus 1. Variance, instead of being represented by the symbol sigma squared, it's represented by the s squared, and the units of variance are the square of the original units. Okay, if you have a sample, you use the sample variance formula instead of the population one. So it just depends what you're working with, and understanding if you're working with a sample or the population, knowing what you've got. So we're going to go ahead and do a quick example using StatCrunch with that same professor salary information that we had. And I'm going to go ahead and go into StatCrunch, and instead of saying that I have all of the professors that work at a school, I'm just going to say that this is a sample of the professors that work at a school, and calculate the sample variance. So just as before, I'm going to go to Stat, Summary Stats, Columns, click Salary. I'm going to go ahead and click the sample size, hold down Control, or if you have a Mac, you would hold down Command, click Mean. This variance is sample variance. So that's what we're using for sample variance, and go ahead and click Compute. Notice there is a little bit of the difference between the unadjusted variance, which is the true variance, and the sample variance. There's a little bit of a difference here, very slight difference. The truth is this one. This is the truth because it's using this as the population. This is saying if this were not the population, if it was just a sample of some bigger population, that's what we could conclude the variance to be. Okay, so in this situation, if this information was a sample, there would be error, and this would be the variance. If this group right here was everybody in the entire population, then this is the truth. The true population parameter of variance is 4.3. So what's the big idea? Today's big idea is that variance and standard deviation both describe the spread of the data relative to the mean. The variance describes the spread in terms of squared units, while the standard deviation describes the spread in terms of linear units. Population calculations and sample calculations use a slightly different formula. The purpose for the two different formulas is to adjust for error between the true population parameter and the sample statistic. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay? This is your teacher, Torres, saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!